Hello, my name is Shu Yang. I'm from Tsinghua University, and it's my great honor to chair this session. So our first speaker is Professor Zhong Wang from Tsinghua University. He will talk about non-Bloch band theory and amoeba. Let's welcome.
Let's go on this. Right. Okay. This non-Bloch band theory is a generalization of the conventional band theory in condensed matter physics to the non-Hermitian or open system. And the amoeba is a geometrical concept which was initially defined in algebraic geometry. But we find this concept to be very useful in our theory. So here is a brief outline of the talk. First of all, I will introduce some basic concept of non-Hermitian physics, and then I'll review the non-Bloch band theory first for one dimension, and then I'll talk about this generalization to actually to arbitrary dimensions, which is based on the amoeba concept. I will also talk about some very recent understanding of why this theory works. So in the standard quantum mechanics textbook, this is often stated that the Hamiltonian of a physical system should always be a Hermitian operator, right? But there is actually a hidden assumption, which is that the system is closed. If the system has an environment, if the system interacts with the environment, then in general, it cannot be described by a Hermitian Hamiltonian. Actually, there are many such systems in nature. For example, in quantum optical, and cold atom, and many other, even the open classical systems, in which the time evolution of the state of the system, which is described by a vector, is generated by an operator which is non-Hermitian. And so such kind of research is generally called non-Hermitian physics. And here is an incomplete table which lists a few systems in which non-Hermitian physics is relevant, and the physical origin of non-Hermiticity in these systems. And here, let me just explain why we should use non-Hermitian operators in the case of open quantum systems. So for the open quantum systems, which interact with the environment, the state of the system is generally not a pure state, so we often focus on the density matrix of the system. Then we consider the time evolution of the density matrix, which under the so-called Markovian approximation can be written in as this equation. So the time evolution of the density matrix is generated as a linear equation. And actually, there's a more transparent way to look at this equation. We can vectorize the density matrix, which means that we write the density matrix as a vector. with of course, the information contained in this vectorized density matrix is the same as the original density matrix, right? And in this way, this mass equation takes the same form as the Schrödinger equation, right? But the important feature is that this effective Hamiltonian, which is called Lewinian in this context, is a non-Hermitian operator. So in general, because it's a non-Hermitian operator, the eigenvalues of the operator is in general complex values. And so in the open quantum systems, we often consider the Lewinian instead of the Hamiltonian, and this Lewinian is generally non-Hermitian, and the mathematical properties of this operator guarantees that there is always a zero eigenvalue. This is physically, this means that there is always a steady state after the very long time evolution of the system. Whatever initial state you have, after a very long time evolution, it converges to the steady state, which corresponds to zero eigenvalue. So in this open quantum system context, the steady state, the rule of the things that is out of power, no electricity. 你好，这个电有没有？这个没有电，好像没有电。So in this open quantum system, the steady state plays the most significant role. So it plays the role of the ground state in it can be regarded as a counterpart of the ground state of the closed system. And because this thank you. So below this zero eigenvalue, all other eigenvalues has a negative real part. So there's a gap between the zero eigenvalue and the other eigenvalues. So this, the inverse of this gap actually determines the relaxation time. So the rule of energy gap in the closed system is replaced by this dissipative gap in the open system. So the key point is that for this open quantum system, what we are studying is a non-Hermitian operator that generates the time evolution. So it has complex eigenvalues. So all the features are very different from what we do in closed systems. And in this talk, we are mainly focused on the band theory. So first of all, let's start from one dimension. Let's briefly recall what's the merit of energy band theory in permission systems. So the band theory is useful for studying a very large system. For example, this is a one-dimensional lattice, and this is a two-dimensional one. So without the band theory, we work with a very large Hamiltonian matrix in the real space. For example, this is real space Hamiltonian for this very simple lattice. So when the system size is very large, size of the matrix is also very large. So we want to calculate the energy spectrum. We should diagonalize this very big matrix. But in the band theory, it becomes very simple. We just do a Fourier transformation of the Hamiltonian to the K space or the Brownian zone. So we only need to work with this very small Hamiltonian matrix. So this is the characteristic equation, and which help us to diagonalize this T-space Hamiltonian. So we obtain the energy spectrum and the eigenstate. So this becomes very simple. So of course, we would like to generalize this success to a non-Hermitian Hamiltonian, right? For example, let's consider this very simple non-Hermitian Hamiltonian, which is non-Hermitian because the hopping is non-reciprocal. The real value of the hopping is larger from right to left than from the left to the right. So this is non-Hermitian. So if we diagonalize this real space Hamiltonian, we find a very strange thing. So the energy spectrum of this Hamiltonian is very sensitive to the boundary conditions. For the conventional periodic boundary conditions, we have this blue energy spectrum. But for the open boundary condition, which means we cut the chain open only in one link, the energy spectrum suddenly becomes this one. So if the system becomes larger and larger, the energy spectrum becomes denser and denser in the complex energy band. But the overall shape does not change very much. So the OBC energy spectrum is very different from the PBC one, even in the thermodynamic limit. So if we work with the conventional band theory, we only get this energy spectrum of the periodic boundary condition. But what we're more interested in the spectrum of the open boundary condition, which is physically more relevant, also in experiment, right? But this cannot be obtained from the conventional band theory. What the paper steady state? So, yeah, here we treat this as a mathematical problem. For example, if you work with open quantum systems, then yeah, you can have a steady state. But for this case, it's quite very difficult to talk about what the steady state is. But we only have we do not have convenience. It's not yet open quantum system. But if we work with open quantum systems with Newtonian, then this kind of Hamiltonian is an important ingredient of the problem. The spectrum of the Newtonian can be obtained from such kind of Hamiltonian, but not exactly the same. Yeah, but so in this case, yes. So this positive imaginary part means gain. So it's the wave function amplitude growth. So this is indeed the case in some physical systems. For example, in some photonic open systems where the botanic mode can gain energy from the environment, which means that the mode can grow. But if you consider an open quantum system described by a mass equation, then the spectrum, the real part will, the imagined part in this context will automatically non-positive. So it's okay. But when you diagonalize the Levinian, then this kind of Hamiltonian is part of that calculation. And of course, this is for non-intelligent systems. If you work with an intelligent system, then you will also need to do the speculative calculations based on this. So there's a metaphor for this sensitivity to the boundary conditions. So if you have this kind of circuit, and you have a battery, then it will light a bulb here, but you just cut the circuit at one point. This bulb will be off, right? So this can be viewed as an open system with energy from the battery, right? So in this kind of open or non-committed system, the boundary conditions is very, very important. For closed systems, usually the boundary condition is not so significant. So if you change the boundary condition a little bit, the ground state of the system usually does not change very much, right? If the system is very big. But for the open or non-committed systems, it is very different. So to be precise, in this case, this high sensitivity of the non-committing Hamiltonian, the X state of non-committing Hamiltonian to the boundary conditions originate from the so-called non-committed spin effect, which means that all the X states of the Hamiltonian are localized at the boundaries. So this is a typical profile of all the X states of a given non-committing Hamiltonian. So this means that the conventional Bloch wave picture fails. So the X state is not a Bloch wave in the standard solid state physics. To precisely characterize this non-committed spin effect, we generalize the concept of breathing zone of solid state to this non-committed system. So we instead of the wave vector k, it's more convenient to work with the phase factor beta, which is e to the I times the wave vector. So the Bloch wave can be written as beta to x, but with the beta living on the unit circle. When the modulus of beta is 1, then this describes a Bloch wave. But the spin effect of the X state means that we should not restrict the modulus of beta to be 1. So if the modulus of beta is not equal to 1, then this means that the X states are localized at the boundary. So all this allowed beta from the curve in the complex plane, which is called the generalized breathing zone, or GBZ. So in the Hermitian limit, this curve reduced to the conventional breathing zone, which is just a unit circle. So given this concept, just defining this concept is not enough. So we have to know how to calculate this from some equation, right? So we need a formula for this GBV. So how to obtain this formula? So this is a very simple example. And there's an intuitive argument which gives this formula in simplest case. So we have this kind of characteristic equation which relates the energy and the momentum or the phase factor. So given an energy of eigenspace, we have several different value of the wave vector or phase factor. So the eigenstate of the system can be written as a combination or superposition of these different waves. In the Hermitian system, in a Hermitian lattice, in one dimension, you have the right moving waves and the left moving waves. So this is very similar. So you have different kind of waves superimposed from a tiny wave, which is the eigenstate of the Hamiltonian. So for open boundary conditions, you require the wave function to vanish at the boundary of the system. Actually, this is impossible. This is possible only when the modulus of the beta 1 and beta 2 are equal in the large size limit. So when the modulus of beta 1 and beta 2 are equal, then the growth rate of the wave of the beta 1 component and the beta 2 component is similar. So they can cancel each other at the right end. But if the modulus of these two rules are different, then the growth rate of beta 1 and beta 2 component is very different. Then if the chain is very long, one component would be much smaller than the other one. Then these two cannot cancel each other. So, which means that such kind of superposition cannot be an eigenstate. So, from this simple argument, we see that in the thermodynamic limit, we should require the modulus of the two rules of the characteristic equation to be equal. So this is the equation of the general green zone. This is the eigenstate of the Hamiltonian. So you are always worried about the positive imaginary part. You can add overall shift to the Hamiltonian. Then you can shift the real part or shift the imaginary part of the Hamiltonian to be always negative. Is that okay? Yeah, you can also shift the imaginary part. It corresponds to overall overall loss, right? It's not normalized, but it's actually this is consistent with many phenomena. For example, if you describe the time evolution of waves, then the wave lost energy to the environment, then the strength of the wave actually decreased with time. So it's okay. But in the open quantum systems, in the context of the Non-Bloch master equation, it is still okay. Actually the trace of the density matrix is still preserved, but it's not because it's not this is exactly this equation. Yeah. Mm. Yeah. Yes. So, the point is that the static state is of our open quantum system is actually not directly comes from this cyclized this very oversimplified non-Hamilton Hamiltonian. Yes, it also exactly in that context. So if you diagonalize this Lewinium, you also find that eigenstate and the spectrum are very sensitive to the boundary condition. But that case is a little bit more complicated than this one. So to illustrate the band theory, I just focus on this simple case. But yeah, so it's not always meaningful to talk about what static state in this one. Right. Okay. And so um, so this is a very simple example with only two roots of the characteristic equation. So in general, there are more roots here of the equation. So, but the basic idea is still similar. So we impose the boundary condition of the open boundary case. So the boundary condition gives us a very big equation, which looks quite complicated, but just like the previous case. The equation greatly simplifies in the thermodynamic limit, which if we order the roots by their modulus, then we find that the middle two modulus should be equal. This equation defines the DBD. So this general equation was derived by these two guys, Yokomido and Murakami. And so all the solutions to this DBD equation from the curve, which is called the DBD. So with this generalized zone, we can do a lot of things. For example, we can calculate the energy spectrum under open boundary conditions in the thermodynamic limit without diagonalizing the big real space Hamiltonian. So we write down the Bloch Hamiltonian, then we take the beta on the GBZ, then the eigenvalues of the Hamiltonian give us this orbital spectrum. And this band theory, based on the generalized Brownian zone, is called Non-Bloch band theory. Actually, the only important difference between this new band theory and the conventional one is the definition of the Brownian zone. In the conventional Bloch band theory, the Brownian zone is fixed. It's in one dimension. It's just always the unit circle. But here, the GBD should be calculated from some equation that we just described. So one of the applications of the Non-Bloch pattern theory is to describe the phenomena called directional amplification. So what's this phenomena? It means that it describes the propagation of some wave signal. So if you input a signal from the left hand, it gets amplified at the right hand. But if you input a signal from the right hand, it is suppressed at the left hand. So it means that the signal are amplified in a directional fashion. So the signal is amplified only towards the right, but suppressed towards the left. So this kind of feature is important in some application in the quantum technology. So if you want to measure some delicate device, you don't want the external noise to affect the device, right? So you need to suppress this noise, but you want to amplify the signal. So this kind of directional amplification is very important. So such kind of so this is also a response phenomenon of the system. So it's described by the Green's function. So this directional amplification at the level of the Green's function, it means that the modulus of the Green's function is different when you change this I and J. So this means that the Hamiltonian here is non-Hermitian. This is very later, right? Because the amplification of a signal means that you work with open system, which gains energy from the environment. So, the important thing is that this Green's function should be written as an integral in the generalized mechanism. So it's an integral in this curve, this generalized mechanism. But if you define the integral, if you write down integral along the conventional mechanism, then it will give you a wrong result. I think I don't have time to go into the details of this formula, but the result is that if you do the integral in the GBD, then it will give you correct value of the Green's function. So another application is in the topology or the principle of the bulk boundary correspondence. So if you have a non-Hermitian Hamiltonian with certain topological features, then it often has a boundary topological mode in the one-dimensional system with chiral symmetry. The topological mode is zero mode. So the zero mode actually can be predicted by the topological number defined in the GBD. So if you insist on defining the topological invariant in the conventional Brownian zone, then again it will not give you the correct number of zero mode. But if you write the topological number as an integral in the GBD, then it predicts correctly the number of zero modes. So these predictions has also been observed in a lot of experiments. And so finally, let me briefly mention the interesting feature of the GBD. At some point of the GBD, there can be some cuts singularity. The GBD is always continuous, but they can be cut, like this kind of this cut in this strange states. So we find that this cup also has some interesting physical meaning. In fact, for non-Hermitian Hamiltonian with the TT symmetry, we find that a smooth GBD without any cut corresponds to the TT exact space with real valued spectrum. But if the GBD has a cut anywhere in this curve, then it means that it is in the TT broken phase, which has complex valued spectrum. So the details are given in this recent papers, which I shall not explain all the details here. Yeah. And yeah, well, in this case, there is no symmetry between positive and the negative part. But of course, you can write a more symmetric model, which it is possible to have such kind of symmetry, but in general, there is no such symmetry from the so here this point corresponds to the k equals to 0, and this corresponds to the k equals pi. So in this particular model, these 2 points not do not be treated as an equal function. The Hamiltonian, if you expand the Hamiltonian at these 2 points, they are different. It's just the feature of this model. Yeah, the model is initially has this symmetry. But this is not a very important feature. Here this does not affect any kind of important equation here. That's not depend on this kind of symmetry between the left and right. It depends more sensitively on the modulus of this curve. If namely whether this GBD is inside the unit circle or outside the unit circle. And so let's move to the higher dimension. So of course we would like to generalize this theoretical framework to the higher dimensional lattice, which helps us to obtain the energy spectrum of a big lattice without doing real space calculations. Instead, we work in the reciprocal space. So let's recall what we have done in 1 dimension. So we write down some ansatz of the eigenstate, then we impose the boundary conditions which give us this simple equation, which does not depend on the details of the Hamiltonian boundary conditions. So we would like to reproduce this in 2 dimensions, but there is a difficulty here. So for a given energy E, there will be infinitely many values of this beta. So this is very different from 1 dimension. For 1 dimension, for a given E, there will be only just a discrete number of beta, right? Here we have infinitely many beta. So the superposition is sum or integral over many components. So it's also very difficult to impose the boundary conditions. So the boundary, in the 1 dimension, the boundary consists of only just 2 points, the 2 ends. But here in 2 dimensions, the boundary is actually the boundary is a 1-dimensional object. So the number of the boundary conditions is proportional to the linear size of the system. So it's also difficult to impose the boundary conditions. But in the 1 dimension, we have noticed that the final equation is very independent of the details of boundary conditions. So there's still hope that similar simplification exists in 2 and higher dimensions. So maybe the equation of the GBZ is still independent of the details of the boundary condition. If so, maybe we can obtain the 2-dimensional GBZ equation by some guesswork. This is what we will do. So there's a hint from the 1 dimension. We have noticed that the modulus of the root is very important. So this equation involves the modulus of the 2 roots of the characteristic equation. So this feature motivates us to this mathematical concept called amoeba, which was defined in 1994 by 3 mathematicians, the Gelfand and the other 2 gentlemen. So this is actually a very elementary object. It's a very natural elementary object. It's defined for a polynomial of several complex variables. So if you have complex variables beta 1 to beta t, then we obtain all the solutions to this equation. And then we take the modulus of each component. Then we take a log. Then all the solutions under this logarithm map is called the amoeba of the polynomial. So here is a very simple example of 1 variable polynomial. So we have this very simple single variable polynomial. Then we find the solution to this equation, right? So we have these 4 solutions. Then we take the modulus of this. These 4 solutions are here. So we take the modulus of these 4 solutions. Then we have, because these 2 has this equal modulus, right? This 3 and this 4 has equal modulus. So the modulus, and then, the logarithm of the modulus only contains these 3 points. So this is called the amoeba of this single variable polynomial. Well, here is a 2-dimensional example. So we have 2 complex variables. So we find the solution to these equations, and then we take the modulus and an algorithm, then in fact, we can really tune the value of z. So the W will follow follow z. W equals to 2 times z plus 1, right? So we plot the modulus of these two components. Then this is called this is the amoeba of these two variable polynomials. So this is very easy to actually in previous talk when I explained the definition of this amoeba, then after the talk, one of the people started sitting in the room, show me some amoeba which he just calculate in the room. So this is a very simple object. So it is called amoeba because the typical shape in 2 dimensions looks a little bit similar to the amoeba, the microbial amoeba. This is amoeba in nature, which is a microbial. So the amoeba has a very thin tentacles going up to the infinity, and sometimes also has a vacuum inside. This is we call it hole. This is very similar to the amoeba in nature, right? And before explaining the application for amoeba, so let's mention that the model we will use are these two ones. For the one-dimensional case, we pick this simple net model with non-intuitive hopping, and in 2 dimensions, it's a generalization of this model. We still have some non-intuitive hopping, and but some intuitive hopping in the diagonal direction. So the Bloch Hamiltonian takes this form, but of course you don't need to remember this kind of equations. And with the definition of amoeba, we can see that in 1 dimension, the GBD equation is actually a statement about the amoeba. So it's of the characteristic polynomial. So it means that the modulus of the middle 2 roots are equal to each other. This means that is the determinant of the geometry of the amoeba, right? So with this, we calculate the amoeba of the 2-dimensional model. We find that whenever the amoeba has a pore, of course, given the energy, we can compute the amoeba. But we find that whenever the amoeba has a pore inside, then this energy does not belong to the energy spectrum of the open boundary condition. So when the core varies, then the energy, for example, for this E4, which belongs to the energy spectrum, there is no core inside the amoeba. But if the energy is outside the energy spectrum, like this E3, then there is always a hole inside. So the 1-dimensional case is actually quite similar. This interval between mu2 and mu3, the mu2 and the mu3 are part of the amoeba, right? And the interval between this mu2 and the mu3 is actually a hole. So if this hole varies, then it means that energy belongs to the energy spectrum. So, somewhat mysteriously, somewhat a little bit mysterious is that this shape of the amoeba tells us the energy spectrum. And so if the amoeba has a hole, then this energy is outside the energy spectrum. Yeah, this is the energy spectrum of a large system obtained from the brute force diagonalization. So it's not quite accurate, but we can say that the E4 is still in the energy spectrum. Yeah. Then there's no need to do this kind of theory because you just diagonalize the Hamiltonian in the conventional Brownian zone. So the more interesting case is the obesity case. So if the amoeba has a hole, then it means that this E is outside the energy spectrum. It's not answered in this slide, but let's go ahead. So, and then let's show the application of this observation. So we can actually this observation help us to calculate the energy spectrum very precisely. For example, we can tune the E along this real axis. So we can observe when does the hole of the amoeba close. This is the band top, right? So for this very large E, we find that there is a hole inside the amoeba. But when we decrease the value of E, the hole of amoeba closes at a certain point. So this is actually the spectral boundary. This is the band top of the spectrum. So the point is that we can calculate, locate this value very, very accurately. So it can be even more accurate than this number. So this kind of observation is indeed very useful in calculating the energy spectrum. But we are not satisfied with this, right? First of all, we would like to prove this observation. This is what you want. And then we also want some more quantitative theory, which, for example, we can obtain not only the energy spectrum, but also the density state of the theory. So we can see that the energy spectrum is denser at some kind of the fun part of the energy spectrum, but it's different than some other part of the spectrum. So we want to precisely describe this density state. So to this end, it's useful to consider the Coulomb potential of the energy spectrum, which is because the energy spectrum is a complex value. So the two-dimensional Coulomb potential is just a logarithm. So we have this in the thermodynamic limit. The Coulomb potential is It's written as an integral of the containing the sensitive state. So if you have this Coulomb potential, then we can obtain the sensitive state by taking the Laplacian. So, so this is the electrostatic analog. So the energy, the eigenenergy that treated like electric charge. Oh, okay. So, so fortunately we have a function called the Rankine function defined based on the amoeba. So, though I think I've a lot to explain the mathematical details of this function. So, just mention that this function takes the minimum either at a single point, or in this case it takes a value minimum at just a single point, or at the inside a hole. Here there is a hole, so the Rankine function takes the minimum in the entire hole. So this is a different way of plotting the Rankine function. So the color means indicate the value of the Rankine function. It's linear in the complement of the amoeba. And what we found is that this Rankine function is actually equal to the Coulomb branch of the energy spectrum of the PBC under theoretical boundary condition with the squares. And the minimization with respect to the value of mu actually give us this Coulomb potential of the OBC system. I think I will not explain the mathematical details that lead to this result. So with this identification of the Coulomb potential as the Rankine minimum, we can obtain the energy spectrum from the Rankine function, and we can very easily prove that when the amoeba has a hole, the energy is outside the spectrum. I think I will not explain the details to you in the talk. We can talk together. Yeah. So with this, we can calculate the sensitive state from the Rankine functions, which is quite accurate. If you can diagonalize the Hamiltonian, the real space Hamiltonian for a very large size, then we find that it will converge to the prediction of the amoeba in the Rankine functions. So this is some linear fitting which indicates that the real space calculation, the brute force calculation, is converged to the prediction of amoeba theory in the thermodynamic limit. The difference between these two potentials goes to zero in the largest size limit. So we can also calculate the generalized Brownian zone based on this amoeba and the Rankine functions. This is the illustration of the generalized Brownian zone in 2 dimensions. With this, we can also define topological numbers in higher dimensions. In this model, we can define the chain number as an integral in the generalized Brownian zone, which indeed correctly predicts the number of the chiral modes. And finally, let me explain in a few minutes some recent understanding of why this amoeba theory works. Actually, we find that the quantum potential of the energy spectrum can be calculated in two different ways. It can be expressed in two different forms. One of the forms is based on the eigenvalues of the Hamiltonian. The eigenvalues of the E minus the Hamiltonian give us this Coulomb potential, but it can also be calculated from the singular values of this E minus H. So the singular value is also a very useful description of a matrix. It's useful in many different contexts, but I will not explain much details of this application, but let's just say that they can be calculated from the singular values of the E minus X. So with this, we can find that the Coulomb potential of the open boundary condition in the case can be written as a summation over the contribution of the single value from the Bloch plus the contribution from the boundary zero mode. So the Bloch mode, the number of Bloch modes grows as the size of the system. But it is just it is the same as the Coulomb potential of the PVC case. The Bloch contribution is insensitive to the boundary conditions, but the zero mode contribution can be written as in this way. The interesting is in general a non-vanishing contribution. This because the factor this zero mode has this exponential form function. So we take after taking the logarithm, it gives us a L factor. So, but the number of the mode is proportional to the area of the boundary. So it's L to D minus 1. So the contribution is order of unity. So in general, this Coulomb potential under OBC and the PVC are different, which means that the spectrum is sensitive to the boundary conditions and the existence of the non-permission skin effect. Now we can do a very simple thing, which is just the similarity transformation to the US-based Hamiltonian. Then we find that the Coulomb potential of the open boundary conditions becomes this Bloch contribution minus the zero mode contribution under the twisted boundary conditions. So this similarity transformation actually does a twist to the Hamiltonian. So this is a single the zero mode of the under the twisted boundary condition. And this Bloch contribution is just the ranking function at this energy, but the boundary conditions comes from the singular value under the twisted boundary conditions, and we find that if we minimize the ranking function, then it's very interesting to see that all the singular values, their mode valid. Then without this single value contribution, that is the OPC Coulomb potential is just a Rankine function. So according to this derivation, the minimum of the Rankine function gives us this Coulomb potential under open boundary condition. And this is indeed consistent with the numerical observation. We find that at the Rankine minimum, in the central hole or in some particular point, we find that the singular value of their mode varies. So this proves that this explains why this minimization of the Rankine function gives us this Coulomb potential and the general free zone and so on. So with this, let's conclude our talk. So we have a non-Bloch band theory based on the generalized free zone, and then there's the amoeba. The geometry object called amoeba plays an essential role. Its shape already tells the energy spectrum. Some function defined as the amoeba contains even more information about the density of state, generalized free zone, and other physical quantities. And of course, there are a lot of open questions. So we still want to further simplify the formulation, and we want to obtain some more straightforward proof of all the results. And we want to go beyond this band theory to study for example, many body physics in this non-commuting and open system. So, thank you.
Thank you very much for the very nice talk. We have time for 1 or 2 short questions. So I have a very short question. So previously you showed the cups, the cusp. So whether the cusp exists or not actually determine whether there is a this one. So whether this cusp exists or not actually determine whether the spectrum is PD, whether the system is PDZ or PD broken, right? So is this the number of cusps important?
Yeah, the number of the cusp is also a relevant quantity, but it actually determines the shape of the spectrum in the PD broken case. So the energy spectrum of can contain several branches, right? So they are branched in the complex plane. So it determines how many branches you have.
Thank you. Questions? Okay, if not, let's thank Professor Wang again for this very nice talk. Thank you.